Somewhere out past Neptune, in the freezing dark, there's a clock. It's been ticking for 4.5 billion years. Nobody wound it. Nobody's watching it. And when it hits 0, we might get less than 2 years warning. We're talking about comets, not the pretty ones that show up in your night sky once a decade, trailing glitter for the tourists. We're talking about the ones we haven't seen yet, the ones still sleeping in the dark, waiting for a gravitational nudge to send them screaming toward the inner solar system, toward us. So, what actually happens if one of them has our name on it? A comet is basically a dirty snowball the size of a city. Ice, dust, frozen gas, and rock, all clumped together since the birth of the solar system, before Earth even had an atmosphere worth breathing. Most of them live in 2 remote neighborhoods. The Kuiper belt, a disk of icy debris beyond Neptune, home to countless frozen relics from the solar system's earliest days. And further out, the Oort cloud, a shell of comets so vast and so distant, it marks the fuzzy edge of the sun's gravitational influence, roughly a light year away in every direction. Out there, they're harmless, frozen, sluggish, minding their own business, some of them barely moving relative to each other for millions of years at a time. But every so often, something disturbs them. A passing star drifting close enough to tug on the cloud, a slow gravitational hiccup from a giant planet. And one of them gets nudged onto a new path, a long, looping orbit that plunges straight toward the sun and straight toward us. Here's the part that should worry you more than asteroids do. Asteroids live in predictable neighborhoods, mostly in a stable belt between Mars and Jupiter. We've mapped most of the big ones. We know their orbits years, sometimes decades in advance, because they've been going around the sun on the same track since before recorded history. Comets don't play by those rules. Long-period comets can take thousands, even millions of years to complete a single orbit, which means most of them are effectively invisible to us until they're already falling toward the sun. And by then, we might have months, maybe less. They're also fast. Comets can slam into Earth's orbit at speeds over 70 kilometers per second, compared to the roughly 20 to 25 kilometers per second typical of an asteroid impact. That's more than twice the velocity. And since kinetic energy scales with the square of speed, a comet hits with dramatically more destructive force than an asteroid of the same size. We like to think we'd see it coming. The truth is, with a long-period comet, we genuinely might not. This isn't hypothetical. Around 12,800 years ago, something changed the climate of the entire planet almost overnight. Temperatures crashed by several degrees in a matter of decades, a blink of an eye in geological time. Dozens of large mammal species, mammoths, giant sloths, saber-toothed cats, vanished within that same narrow window. Some scientists think a fragmenting comet, exploding in the atmosphere rather than gouging a crater into the ground, triggered a sudden cooling event that reshaped life on Earth. The evidence is still debated, and not every researcher agrees on the cause. But the pattern is chillingly familiar. No crater, no warning, just catastrophe from above. And we already know what a smaller version of this looks like, because it happened within living memory. In 1908, over Tunguska, Siberia, an object, likely a fragment of a comet, detonated in the sky with the force of roughly 1,000 Hiroshima bombs. It flattened 80 million trees across 2,000 square kilometers of forest, snapping trunks like matchsticks in every direction from the blast center. There was no impact site, no crater, just a shock wave, a blinding flash, and a forest that no longer existed. Now imagine that airburst happening over a city instead of an empty forest. Let's build the worst-case scenario. Not for drama, for understanding. A comet, a few kilometers wide, is spotted late. Too late for a mission to intercept it. It enters the atmosphere at extreme speed and either detonates mid-air with city-flattening force or slams into the ocean, since water covers most of our planet's surface. An ocean impact sounds safer. It isn't. The impact vaporizes water and rock instantly, launching a plume of superheated debris into the upper atmosphere. Mega tsunamis race outward in every direction, capable of drowning coastlines thousands of kilometers away within hours, and the real damage happens after the splash. Dust and sulfur particles blasted high into the stratosphere start blocking sunlight across the entire globe. Global temperatures drop, sometimes by more than 10 degrees Celsius. Crops fail across multiple growing seasons in a row. This is what scientists call an impact winter. Not science fiction, but the same basic mechanism believed to have ended the age of dinosaurs 66 million years ago. Supply chains break down within weeks. Agriculture collapses across entire continents in a matter of seasons, and civilization, which depends on stable weather and predictable harvests far more than we like to admit, gets pushed to its breaking point, not by war, not by disease, but by a rock that's been falling toward us since before humans existed. That's the nightmare version. Here's the good news. We're not sitting around waiting for it to happen. Right now, telescopes around the world are scanning the sky every single night, cataloging near-Earth objects and calculating their orbits decades into the future. Survey programs sweep the same patches of sky over and over, comparing images to spot anything that's moved. Programs like NASA's Planetary Defense Coordination Office exist for exactly one reason: to make sure nothing sneaks up on us. They've already found and tracked the vast majority of large, civilization-threatening asteroids near Earth. Comets remain the harder problem, but even there, our detection window keeps growing every year as telescopes get sharper and surveys get faster. And in 2022, we proved something remarkable. NASA's DART mission deliberately crashed a spacecraft into an asteroid called Dimorphos, not because it threatened Earth, but to test whether we could actually change an object's trajectory in space using nothing but a controlled collision. It worked. We nudged a moon. On purpose. The impact shortened Dimorphos's orbit around its parent asteroid by over half an hour, far more than scientists expected. That single test changed the entire conversation around planetary defense. We're no longer just watching the sky and hoping. We're building, testing, and refining the tools to actually do something about it, years or even decades before impact. So, should you worry? Here's the part where we pull you back from the edge. The odds of a civilization-ending comet impact in any given century are astronomically small, genuinely astronomical, in the literal sense. Most large comets that could threaten Earth have long, stable orbits we're actively tracking, revisited and recalculated with every close pass. The truly dangerous scenario, a large, undiscovered long-period comet appearing with little warning, is rare enough that you're statistically far more likely to be affected by almost anything else on this planet, from a volcano to a heat wave. Detection technology keeps improving every year, with new observatories coming online specifically built to catch faint, fast-moving objects sooner than ever before. Deflection technology is no longer theoretical. It's proven, tested, and sitting in the toolkit for the day we might actually need it. And the scientific community takes this threat seriously enough to fund entire agencies dedicated to watching, calculating, and, if it ever comes to it, redirecting. The clock out past Neptune is still ticking. It has been for billions of years, indifferent to everything happening down here. But for the first time in Earth's 4.5 billion year history, there's a species down here actually looking up, actually counting the seconds, and actually building a way to stop it. That's not nothing. That might be everything.